This is the third video in this video series about multiple samples with a quantitative response variable. In the first video, we looked at a two-sample test with original scores. In the second, we looked at a two-sample test with ranks. And now we're going to look at a two-sample normal scores test. We saw that the Fisher-Pittman type randomization test can be used with ranks. It can be used with any transformation. So a natural extension is to use normal scores. This can be especially useful for Plato-Kurtic distributions when normal scores can provide higher power than other methods. As a reminder, a Plato-Kurtic distribution is one that has low kurtosis compared to the normal distribution. Therefore, it has a lower peak and lighter tails. The required packages to follow along with this presentation in R are NP-Learn and Coin. We have random samples from two populations. Two existing independent populations might be compared, in which case we literally draw a random sample from each population, or we might draw a single random sample from an existing population, randomized to conditions so that one of the samples represents a potential population. We have independent observations within each sample and a quantitative response measure. If you watched the previous two videos, this should all look familiar to you. The setup is the same. What's different is the transformation we're going to use. With identical distribution shapes, we can have a null hypothesis that the two medians for the two populations are equal. In this case, I'm using the same example that I've been using in this video series with prosodic reading and repeated reading, and so I've used subscripts here of P and R. In general, you could think of it as 1 and 2. The alternative hypothesis for this particular example is that the median of the prosodic condition is going to be less than that of repeated reading because we're focusing on numbers of errors and we think prosodic reading will reduce the number of errors. If we do not have the identity of shapes that is required in order to test the two medians, then we can look at the probability that the smallest value will come from the prosodic condition if we select a score at random from both the prosodic and repeated reading conditions. The probability will be 1/2, meaning it's equally likely that the lowest score will come from one condition as it will the other. But the alternative hypothesis is that there's a higher probability the lower score will come from the prosodic reading condition. This is very consistent with most research hypotheses, even though most research hypotheses that you see focus on location. We can focus on these kinds of probabilities. That reduces the number of conditions that we need. I have demonstrated van der Waerden normal scores in previous video series. In the two-sample case, we combine all scores from both conditions, and we create normal scores. I've labeled that here Z because they come from a normal distribution, such that the probability of obtaining a normal score being less than our observed normal score is equal to I divided by n plus 1. If you watched the previous video series on normal scores, you know that this fraction at the end is telling us how many times we have to divide up the normal distribution in order to obtain all the normal scores that we need. For the one sample case, we actually have to divide up many more times than the number of scores we need because we only use positive normal scores. But in the two sample case, we use both positive and negative normal scores. That means we don't have to divide up the normal distribution as many times in the two sample situation as we do in the one sample situation in which we have the same sample size. So if we need 4 normal scores, for example, we have to divide up the distribution into 5 equal parts. If we need 10 normal scores, we need to divide it up into 11 parts. We replace the original scores with the normal scores in order. That is, the lowest original score will get the lowest normal score, which will be a negative normal score, and the highest original score will get our final and highest normal score. We then put the normal scores into our conditions to correspond to how the original scores were in those conditions. Here's an example. I'm going to use the prosodic element study data from the previous video. So the prosodic condition here, we obtain scores of 2, 13, 11, and 15. The repeated reading condition, 17, 14, 20, 18, and 28. And then I put them all together. I combine them here on line 3. And then this is the new part. We now calculate the normal scores. I'm using here the normal scores function from the NP-Learn R package that I have created and is available on GitHub. If you look at these normal scores here, you see that they include both negative and positive values. In fact, we see symmetry. We see that the largest negative value, that is the smallest value, is just the negative of the largest value. Now we place these into their corresponding conditions. So these first 4 normal scores that I've created here will go into the prosodic condition, and the last 5 will go into the repeated reading conditions. Notice that when I listed the normal scores here, I listed them in an order that already corresponded to the scores from the prosodic and repeated conditions consecutively, because that's the way I assembled it up here. We now let T be the sum of the normal scores in the smallest condition. In our case, that's the prosodic reading condition. We calculate T for all possible combinations of scores. That is, we take our original scores, we create all the possibilities for those original scores, we calculate the normal scores and put them in according to their original scores for every combination, calculate T by summing up the scores in the smallest group, and then sort the values of T. We can then calculate the cumulative probability. So the smallest value we have here for T is negative 2.9, followed by negative 2.65, and so on. Notice the probability is the same for each of those, and I see the probability here stays the same, and that we don't really have any repetitions until we get to, oh, nope, I missed one. Here's one. We have repetitions right here. So the probability of getting a negative 2.12 is actually going to be twice this single listed probability. But more importantly, we've created a cumulative probability column here from the bottom up and another cumulative probability from the top down. We're going to be doing a lower tail test. Here is our observed test statistic. I just created a sum of all the normal scores that are in the prosodic condition, and that's negative 2.648. So if I go back here, I find that right here, and that has a cumulative probability of 0.0159 or 0.016. So that is our p statistic. When we did this with both original scores and ranks, we also arrived at p of 0.016. The reason that these are all turning out to be the same is because we're in the very tail of the distribution. Once we get beyond that tail, these p-values are going to start differing. So I don't want you to be left with the impression that the p-statistic is always the same using all 3 methods. That wouldn't make sense because we should be getting different kinds of power for different kinds of transformations. Here's an R function. We can use the coin package. And so notice that what I've done here is set this up so that we have a factor, and that factor is going to have prosodic and repeated reading conditions. That's a categorical variable. R always considers factors categorical variables. Here I've obtained the score by combining, and here I'm going to do the normal test. Notice that there is no need for me to create normal scores. That's done automatically as part of this normal test. I indicate that the score is a function of condition, that I need a lower tail test, and that I want an exact test. And what I get is the p-statistic that we calculated by hand. Now, one item of note, here you see a z, and if you compare this z to back here, you say, oh, they're different. This is not the z that we actually calculated back here as our test statistic. This is the z that would be used if we were doing an asymptotic approximation. That is, if we were looking for a z-score on the normal distribution to give us an asymptotic p-value, but that's not the case. So this is a little misleading because here we have the z for the asymptotic approximation, but this is the p-value for the exact test. We don't need the z here because we're doing that exact test. We do have three options with the coin function. We can use an exact test, a Monte Carlo approximation, or asymptotic. The rule that I use is to use an exact test when possible, but if it can no longer do an exact test, I switch to the Monte Carlo approximation. Eventually, the Monte Carlo approximation and the asymptotic approximation will converge on the same value. So what is that value? Well, we'll look at that in a moment, but first let's talk about a comparison to the t-test and the Fisher-Pittman test and the Wilcoxon-Rank sum test. We now have our fourth possibility. We can choose to do the parametric t-test, we can choose to do the two-sample test with original scores, or we can choose to do the two-sample test with ranks. This test is asymptotically more powerful than any of these for light-tailed distributions, that is, when we have low kurtosis. This test asymptotically will have the same power as the T and the Fisher-Pittman type test with a normal distribution. In other words, when you're using normal scores because you think you might have a light-tailed distribution, but it turns out that actually it's close to normal, you don't lose anything. This test is computationally intensive with larger sample sizes because we're using just as many scores as we had original scores. Here is that large sample approximation that I alluded to a moment ago. That is what we would get if we were to do an asymptotic approximation. By the central limit theorem, our test statistic t, the sum of normal scores of one of the samples, will approach a normal distribution. And under the null hypothesis, that normal distribution will have a mean of 0. The standard deviation of our test statistic will be the square root of the product of the two sample sizes divided by the overall sample size minus 1, and then we multiply all that by the sum of z squares divided by the sample size. So those are the known means and standard deviations, and they are based upon the number of scores. Well, you may look here and say, well, we also need to know the z's, but remember, if you know the number of scores, you know the z's. So even though we're looking like we're doing a parametric test because we're using a normal distribution, it is a non-parametric test because these particular parameters of mean and sigma have nothing at all to do with the null hypothesis. The sample sizes are the only things that are involved in this mean and standard deviation. So even though you're doing an approximation, you're still doing an approximation for a non-parametric test. We now have the t-test, the original scores randomization test, the rank test with randomization, and the normal scores randomization test. How do we choose? If we know something about our distribution, the choice is obvious. If we don't, we may want to choose a procedure in which we know that the asymptotic relative efficiency will never get to be too low, but could get quite high. For that reason, I consider the normal scores to be a very good choice if we have the computational power. If not, then I would consider ranks to also be a good choice because the asymptotic relative efficiency under the normal distribution is not very low, and the asymptotic relative efficiency with other distributions can be large.